These two objectives will be covered in 2 parts. At the end of this Part 1 video, you should start to be able to define atomic and ionic radii, ionization energy, electron affinity, and electronegativity, as well as compare the periodic trends of atomic radii, ionization energy, and electronegativity, as well as stating the reasons for these variations. Chapter 5, Section 3, Electron Configuration and Periodic Properties. So far, you have learned that the elements are arranged in the periodic table according to their atomic number, and that there is a rough correlation between the arrangement of the elements and their electron configurations. In this section, the relationship between the periodic law and the electron configurations will be further explored. Atomic radii. Ideally, the size of an atom is defined by the edge of its orbital. However, this boundary is fuzzy and varies under different conditions. Therefore, to estimate the size of an atom, the conditions under which each atom exists must be specified. One way to express an atom's radius is to measure the distance between the nuclei of 2 identical atoms that are chemically bonded together, then divide this distance by 2. As illustrated in Figure 5-12 or on the screen now, atomic radius may be defined as 1/2 the distance between the nuclei of identical atoms that are bonded together. Periodic trends. Figure 5-13 on page 141 of your text or on the screen now gives the atomic radii of the elements, and Figure 5-14 on page 142 of your text represents this information graphically. Note that there is a gradual decrease in atomic radii across the second period, from lithium, Li, to neon, Ne. The trend to smaller atoms across a period is caused by the increasing positive charge of the nucleus. As electrons add to the s and p sublevels in the same main energy level, they are gradually pulled closer to the more highly charged nucleus. This increased pull results in a decrease in atomic radii. The attraction of the nucleus is somewhat offset by the repulsion among the increased number of electrons in the same outer energy level. As a result, the difference in radii between neighboring atoms in each period grows smaller. Group trends. Examine the atomic radii of the group 1 elements using the graphic on the screen now from Figure 5-13 on page 141 of your text. Notice that the radii of the elements increase as you go down the group. As electrons occupy sublevels in successively higher main energy levels located farther from the nucleus, the sizes of the atoms increase. In general, the atomic radii of the main group elements increase down a group. Now examine the radii of the group 13 elements. Although gallium, Ga, follows aluminum, Al, it has a slightly smaller atomic radius than does aluminum. This is because gallium, unlike aluminum, is preceded in its period by the 10 d block elements. The expected increase in gallium's radius caused by the filling of the 4th main energy level is outweighed by a shrinking of the electron cloud caused by a nuclear charge that is considerably higher than that of aluminum. Ionization energy. An electron can be removed from an atom if enough energy is supplied. Using A as a symbol for an atom of any element, the process can be represented as follows. A plus energy reacts to form A plus 1 and a free electron. The A plus 1 represents an ion of element A with a single positive charge, referred to as a 1 plus ion. An ion is an atom or group of bonded atoms that has a positive or negative charge. Sodium, for example, forms the Na plus 1 ion. Any process that results in the formation of an ion is referred to as ionization. To compare the ease with which atoms of different elements give up electrons, chemists compare ionization energies. The energy required to remove one electron from a neutral atom of an element is the ionization energy, IE, or the first ionization energy, i.e. 1.
An ion is an atom, radical, or molecule that has gained or lost one or more electrons and has a negative or positive charge. For example, When a sodium atom loses an electron, it becomes a sodium ion. Sodium ions have a positive charge. Other atoms become ions by gaining an electron. For example, when a chlorine atom gains an electron, it becomes a chloride ion. Chloride ions have a negative charge.
To avoid the influence of nearby atoms, measurements of ionization energies are made on isolated atoms in the gas phase. Figure 5-15 on page 143 of your text, or on the screen now, gives the first ionization energies for the elements in kilojoules per mole, and figure 5-16 on page 144 of your text represents this information graphically. Period trends. In figures 5-15 and 5-16, examine the ionization energies for the first and last elements in each period. You can see that the group 1 metals have the lowest first ionization energies in the respective periods. Therefore, they lose electrons most easily. This ease of electron loss is a major reason for the high reactivity of the group 1 alkali metals. The group 18 elements, the noble gases, have the highest ionization energies. They do not lose electrons easily. The low reactivity of the noble gases is partly based on this difficulty of electron removal. In general, ionization energies of the main group elements increase across a period. This increase is caused by increasing nuclear charge. A higher charge more strongly attracts electrons in the same energy level. Increasing nuclear charge is responsible for both increasing ionization energy and decreasing radii across periods. Note that, in general, nonmetals have higher ionization energies than metals do. In each period, the element of group 1 has the lowest ionization energy, and the element of group 18 has the highest ionization energy. Group trends. Among the main group elements, ionization energies generally decrease down the groups. Electrons removed from atom of each succeeding element in a group are in the highest energy levels, further from the nucleus. Therefore, they are removed more easily. Also, as atomic number increases going down a group, more electrons lie between the nucleus and the electrons in the highest occupied energy levels. This partially shields the outer electrons from the effect of the nuclear charge. Together, these influences overcome the attraction of the electrons to the increasing nuclear charge, removing electrons from positive ions. With sufficient energy, electrons can be removed from positive ions as well as from neutral atoms. The energies for removal of additional electrons from the atom are referred to as the second ionization energy, i.e. sub 2, third ionization energy, i.e. sub 3, and so on. Table 5-3 on page 145 of your text, or on the screen now, shows the first 5 ionization energies for the elements of the first, second, and third periods. You can see that the second ionization energy is always higher than the first. The third is always higher than the second, and so on. This is because as electrons are removed in successive ionizations, fewer electrons remain within the atom to shield the attractive force of the nucleus. Thus, each successive electron removed from an ion feels an increasingly stronger effect of nuclear charge, which is the nuclear charge minus the electron shielding. The first ionization energies in Table 5-3 show that removing a single electron from an atom of a group 18 element is more difficult than removing an electron from atoms of the other elements in the same period. This special stability of the noble gas configurations also applies to ions that have noble gas configurations. Notice in Table 5-3 the large increases between the first and second ionization energies of lithium, Li, and between the second and third ionization energies of beryllium, Be. Even larger increases in ionization energy exist between the third and fourth ionization energies of boron, B, and between the fourth and fifth ionization energies of carbon, C. In each case, the jump in ionization energy occurs when an ion assumes a noble gas configuration. For example, the removal of one electron from a lithium atom, which has a configuration of helium-2s1, leaves the helium configuration. The removal of 4 electrons from a carbon atom, which has a configuration of helium 2s2 2p2, also leaves the helium configuration. A bigger table would show that this trend continues across the entire periodic system.
An ion is an electrically charged atom. If the ion has more protons than electrons, it is a positive ion or cation. If it has more electrons than protons, it will be a negative ion or anion. Ionization is any process that causes a gaseous atom to become electrically charged. A sodium atom is ionized when energy is added to remove an electron. The amount of energy required to do this is called the ionization energy. Ionization energies differ among atoms. This table shows the ionization energy required to remove the first electron from an atom. Once an electron is removed from a neutral gaseous atom, the atom becomes positive, and its remaining electrons are held more tightly to the positive nucleus. Additional ionizations to remove a second or third electron require increasingly more energy. A gaseous atom can also ionize by gaining electrons. Most atoms release energy in this process. This energy represents the atom's electron affinity. Electron affinity can be thought of as the tendency of an atom to accept electrons. Atoms with high electron affinities tend to form negative ions more easily than those with low electron affinities.
At this point, you should start to be able to define atomic and ionic radii, ionization energy, electron affinity, and electronegativity, and compare the periodic trends of atomic radii, ionization energy, and electronegativity, and state the reasons for these variations.